So I made a video on normal mapping in GameMaker a few weeks ago, and in that video I talked about something called a TBN matrix, which is needed in order to orient the normal vectors from the normal map on the surface of the object that you're rendering. And also in that video I said I would talk about how to calculate the TBN vectors for a vertex or for a surface some other day. And I made the executive decision to calculate the ones for the models I was using in that video ahead of time, load them in from a file, and basically not worry about them again. And today is that some other day. Today we're going to talk about how to calculate the TBN vectors of a mesh, and that is something that you will be able to make use of to apply normal mapping to any 3D mesh that you want. So this should go without saying, but you should probably go watch the normal mapping video first if you haven't done that already, if you don't know how normal mapping works. I talked about some other things in detail in that video that I don't really want to spend a great deal of time rehashing now. So tangents, bitangents, and normals. These are three vectors that are calculated for every surface and/or every vertex. You can think of it as a mini coordinate system that you can use to align the normal map values with any point on a 3D mesh. And one of those values we already know. So we are pretty familiar with how normal vectors work in 3D, right? It is just the vector that is pointing out perpendicularly from a surface. In this little demo scene, I can hit the spacebar and I can reveal the surface normals of each triangle sticking out from the middle of them. We can look at that little icosahedron model. We can look at the sword and the master sword sheath, and we can see the normal vector sticking out of every triangle there. That's a lot of fun, right? The tangent vector is, as the name implies, a vector that is perpendicular at a 90-degree angle to the normal vector. It is tangent to the surface, and calculating that is a little bit trickier. I made a video on calculating normals a while ago. It's not that hard. You just take the two edge vectors and find the vector which is produced by the cross product of those two edge vectors. And then if you want, you can apply some fancy normal smoothing to the to all the vertices if you want. And the fact that there is one and only one normal vector for any given triangle really makes the job easier there. Unfortunately, tangents are not quite so straightforward. So for any surface, if you have a surface and a normal vector, you can have infinitely many tangent vectors. You could just take one tangent vector and just rotate it any amount, and that will be an equally valid tangent vector. So because it's going to really, really help us out if all of our tangent vectors and our bitangent vectors are generally going the same way, we are going to have to use a few more interesting mathematical tricks in order to work this out. And also the bitangent vector is a second tangent vector which is perpendicular to both the normal and the first tangent vector. That's actually a little bit less important because much like the up and forward vectors of a camera, if you have the normal vector and the tangent vector, it's pretty easy to just calculate the bitangent by taking the cross product of those. Because, as always, the cross product is a math function which will produce a vector 3, which is perpendicular to two vector 2 inputs, assuming that one exists. So the derivation for the math that I'm going to discuss today is a little bit complicated, and because I want this video to be at least somewhat approachable to people who aren't, like, way interested in higher level math, or at least linear algebra math, I'm going to just give a rather quick summary of what we're going to do before we get into writing code. So given some amount of information about a triangle, so we're going to look at pieces of information about a triangle such as the two edge vectors and the gradient of the texture UVs, the texture coordinates on each vertex of each triangle.
Hey.
And if it makes it easier, you can think of the edge vectors as obviously the like P2 minus P1 and then P3 minus P1. That's the two edges of the triangle in space. You could think of the gradients or the deltas of the texture UVs as the same thing, but for the texture coordinates. So the texture coordinates of the second point of the triangle minus the texture coordinates of the first, and the texture coordinates of the third point minus the texture coordinates of the first. I'm going to refer to that as delta U and delta V, which is probably going to get a little tiring to say out loud a million times in this video, but that is the terminology that you will often see used by other people describing this, and if you wanted to find out more about this, I want to give you terms that you'll be able to Google. Anyway, given these inputs, we can work out a series of equations, two equations which we can solve for, which would be the first edge of the triangle is going to be equal to delta U multiplied by the tangent vector plus delta V multiplied by the bitangent vector. And the second edge of the triangle is going to be similar. The second edge will have a value equal to delta U of the second edge of the triangle multiplied by the tangent vector plus delta v of the second edge of the triangle multiplied by the bitangent vector. And I don't know about you, but solving systems of equations wasn't the most fun I ever had in math class in high school. But fortunately, people who are smarter than me have already done this work, and by doing some tricks such as substituting matrices for some combinations of some of the vectors in this equation, and then writing out the components of each vector the long way, you can turn that system of equations into a single matrix operation. So a matrix containing the edge vectors is going to be equal to a matrix containing the texture UVs multiplied by a matrix containing the tangent and bitangent vectors. And then you can shuffle that around. You can multiply both sides of that equation by an inverse matrix to get the tangent and bitangent vectors on their own. And if you're into matrix math, you should know what to do from here. And if not, don't worry, I'm going to walk you through it. This, like the edge of this sword has been spinning in front of my face in this camera view, like that whole time while I've been talking through that. And it's just distracting me a little tiny bit, and I should probably make it stop. Right, so I guess I should go through this test project a little bit. It's pretty similar to what I had in the test project that I had for the normal mapping video itself, but I am loading vertex buffers out of files which contain only 3D position, normal, text chord, and color information. I am not loading them out of files already containing the tangent and bitangent information. That is, of course, what I will be calculating in this video today. And I've also gone and added a couple of little functions which will generate, like, I guess I would call them normal vector wireframes. Just going through each triangle and like creating a bunch of lines, drawing a bunch of lines that correspond with the normal vectors. I've done that for the like just the normals with the original vertex format, and I've also got a version of this function to work with the normals, the tangents, and the bitangents, which I'll just be using for demonstration purposes. I'm not going to spend too much time explaining that in this video, but if you're curious on doing something like that yourself, you may wish to look through this code for how that's going to be done. Let's see. So let me go and create myself a new function. I'm going to call it, let's say, calculate tangents. This is going to be a function which will take a couple of inputs. By a couple of inputs, I actually just mean the vertex buffer and the vertex format. We'll be able to call this function something like, let me say, VB underscore sword TBN is going to be calculate tangents. Calculate tangents. The vertex buffer can be the original VB underscore sword, and the vertex format in question is going to be the vertex format, which contains a position, normal, text chord, color, and two additional colors, which will contain the tangent and the bitangent. By the way, last time I did say that you can't really just use anything you want for a like a vertex attribute, and someone in the comments did say that you actually can if you use some of the advanced vertex format functions. Vertex format, I believe, what is it? Custom. This function, that's kind of a whole thing. I haven't messed around with that on my own. Terrahanula usually knows what he's talking about, so if he says that's how it works, I'm going to assume that it is. But all the same, in this video, because I don't want to go messing around with crazy vertex formats, I'm just going to go and stick with the additional color attributes, which is going to mean I'm going to have to do a little bit of extra calculating when I write the new vertex buffer. Anyway, sword sheath. I'm not going to generate TBN for the ground. We're not going to be worrying about the ground. VB sheath TBN and VB sphere TBN, and we're going to feed the original vertex buffer into that. We're going to turn it into a regular buffer. We're going to read out all of the triangle data, and then we're going to feed the updated information into a new vertex buffer. So let's say original data is going to be buffer create from vertex buffer. That vertex buffer can be vbuff. The type can be buffer fixed, which is kind of the default buffer type. The alignment can be 1. I'm going to also want to say our new vbuff is going to be vertex create buffer. vertex begin so that we can start writing information into new vbuff with the specified vertex format. Once we're done, at the bottom, vertex end. Of course, we're going to want to buffer delete. This won't delete the original vertex buffer. It'll just delete the copy or the regular buffer. And at this point, we might as well return new buffer like this. Worth mentioning, buffer create from vertex buffer will not work on frozen vertex buffers. So if you're going to do this, you're going to want to do it before you freeze the vertex buffer, because once you freeze the vertex buffer, you can't do crazy things like this to it. Let's see. So it would help to know the number of vertices inside this original vertex buffer, and I'll say vertex count equals vertex get number. So the vertex get number size will return the number of vertices in a vertex buffer. Probably the easiest way to get that value. Next, we're going to need to iterate over this this like list of vertex information things. You can do that any number of ways. You can use a for loop, you can use a while loop, you can use a repeat loop. I'm just going to use a repeat loop because it's easy and because we don't need to keep track of a like an index position or anything like that. I'm going to actually not loop over this vertex by vertex, but triangle by triangle, which means that I'm going to have to divide vertex count by 3. And next I'm going to do a little bit of busy work. So I'm going to read out all 9 vertex attributes from each vertex 3 times for each vertex of the triangle. And that's going to be a lot of code that looks like var x1 equals buffer read original data. I'm already regretting using a variable name that's that long. The type can be buffer f32 because most things in a vertex buffer are 32-bit floats. We can do that for y and z. Normals are next, so maybe nx1, nx2, something like that. Texture coordinates can be u and v, and the color value can be a single u32 for color, which is going to contain red, green, blue, and alpha. And I'm going to have to do this 3 times. Okay? Like I said, this is kind of just like busy work. So next, I did mention that I'm going to want the edge vectors of a triangle. I'm going to say this doesn't have to be normalized, just because we'll normalize everything at the end anyway. In my video on calculating the normals of a triangle, I did use like object-oriented vector GameMaker code because I thought it was convenient to be able to just say like edge 1 cross product edge 2 and that kind of thing. But let's just say that I don't think that's going to save us that much time this time around, so I'm not going to do that. So instead I'm going to do it kind of the classic GameMaker way. This is going to be e1x edge 1x is going to be equal to x2 minus x1, e1y, y2 minus y1, and then e1z, so the z component of the first edge is going to be z2 minus z1. Same thing for the second edge, that's going to be the third vertex, subtract the first vertex. And I also said I was going to want to do something similar with the texture UVs. So I guess I can say var e1u is going to be u2 minus u1, e1v, v2 minus v1, and same thing for the second edge. So those are going to be our inputs into the big old calculation I'm going to do. So first, I will need what I suppose we can call the determinant of the matrix containing the like the delta UV values, the edge UV values, whatever. I'm gonna say var determinant det is going to be equal to 1 divided by the quantity of let's say e1 e1u multiplied by e2v minus, I keep e2v minus e1v multiplied by e2u. And this is going to be a Again, if you're into matrices, this will be the determinant of that matrix. Otherwise, you can just think of it as a scale factor that we will be multiplying a bunch of values by. This determinant value can, of course, be used to invert a matrix, and I'm just going to use that to multiply by a series of values, which we can use to figure out what I'm going to call Tx, Ty, and Tz, which is going to be the tangent vectors for a triangle. Tx is going to be det multiplied by, let me squint at my notes to make sure that I'm copying this down right. Let's say e2v multiplied by e1x minus e1v multiplied by e2x. That all in parentheses, so that quantity. And the y component, the z component of this tangent vector are going to be the edge y component and the edge z component. And like these values here, those are going to be the same throughout. You can also do, if you want, the bitangent values, which is going to be similar, but instead of the second edge v texture coordinate multiplied by the first edge, we're going to be saying e2u, so the horizontal texture coordinate of the second edge, multiplied by e1x, e1y, e1z, and then we're going to be subtracting e2, or e1v, rather, e1u, rather, multiplied by the xyz of the second edge. And this is also going to want to be toss a negative in front of that. You can, of course, rearrange this and get rid of a negative by simply doing something like this, because addition is commutative like this, and this will give you your bitangent vectors. So next, these tangent and bitangent vectors are going to not necessarily be having a magnitude of 1, and we like our vectors which represent directions like this rather than positions to have a unit length of 1. So we can just normalize these vectors. You do that, of course, by taking the unit length of that vector and dividing all components by it. Can do the same thing with the bitangent. So bx, by, bz, like this. And now we have our normalized tangent and bitangent vectors. So if your vertex format only calls for a like 3 actual 12-byte 3 float normals for normal tangent and bitangent, you can just stop here. But because I am feeding this into my vertex buffer as color, as a color, and we'll have to do some encoding and decoding normals as color tricks. Let's see. Each of these vectors can have a value between -1 and +1. So I'm going to want to, for each of these tx, ty, tz, etc., I'm going to want to divide by 0.5. I'll just say tx equals tx divided by 0.5. I'm going to want to add 0.5, and because GameMaker likes its colors to have a range between 0 and 255 rather than 0 to 1, I can multiply by 255, and same thing for y and z. Like this. And to store this as a single color value composed of red, green, and blue, I can say tangent color is going to equal make color RGB, red being TX, green being TY, blue being TZ. We can do the same thing for the bitangent if we want. BX, BY, BZ, bitangent color, like this. And now all of the annoying math is finished, and it is just a matter of feeding this data back into a vertex buffer. And that's going to mostly involve a couple of steps that look something like vertex position 3D, new v buff. We are, of course, going to want to stick the x1, y1, z1 back in without modification. Vertex normal, the original normal vector without modification. So nx1, ny1, and z1. Vertex text chord, u1 and v1. Vertex color is going to be a little bit involved because the like c1, c2, c3. This is just a 32-bit integer containing alpha and color information, and vertex color expects like color to be separate from alpha. So I can say c1. Let's binary and against 0 by 0, 0, f, 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 just to extract the color channel information out of that value, and the alpha can be c1 shift to the right by 24 bits divided by 255. There are other ways to do this, by the way. You could read out red, green, blue, and alpha values individually from the original buffer if you'd like. Anyway, that's the original vertex data. I'm going to now want to vertex color a second time. And now for the color, I'm going to just insert the tangent color because this is now formatted as a GameMaker color code, but it contains information that can be converted back into a normal vector, which is another thing I did discuss in the last video. By the way, that BTX, that doesn't need to be there. And the alpha doesn't matter because we're not going to be looking at it when we convert that value into a tangent or bitangent vector, but I'm just going to set it to 1 because it makes me feel good. And same thing for the second vertex. And the same thing for the third vertex. And I should actually also write in the bitangent color. If I want that to be included, which I do. I should mention, by the way, that GameMaker did recently, I believe, introduce in an update a function that is buffer copy with a stride, and this is effectively the same thing as buffer copy, but you can add some like blank space in between some intervals in the buffer. And if you use that instead of using the vertex buffer functions to build a new vertex buffer, you can save a little bit of work where you don't need it, like rewriting the same position and whatever information. But that involves a bit more when it comes to things like iterating over the buffer and actually keeping track of your position in the buffer, which I didn't really feel like doing today, so I didn't use that. But it is something that may be worth mentioning. And that should be it from here. Oh, I'm going to want to like return new vbuff, not new buffer, aren't I? From here, we can vertex end, and we can return our new vertex buffer, and we can carry on as usual. So let's see. I do want to visualize this with the like the normal vector wireframes and whatnot. So I'm going to use the generate TBN wireframe functions here, and I guess I'll say like sphere wire TBN and whatever. I'm going to need to generate the that vertex buffer from the ones that we actually modified that actually does contain the TBN information. When I go into the draw event, when we just look at the vertex buffers, nothing is really going to change. Because, like, generally speaking, if you submit a vertex buffer with attributes that the shader doesn't use, the shader will just ignore it and carry on with its day. But this will be a vertex buffer that you can use with an actual normal map if you want. Before I do that, because I do still have the normal mapping code in this project, let me just say that when you hit the spacebar, we will draw those vectors on the surfaces of the shapes. And assuming that I didn't copy anything wrong anywhere, which it looks like I did, Okay, I'm just trying to generate wireframes from the wrong vertex buffer. I'm glad it was something silly and not something mathy. Also, this doesn't quite look right. This should be VB underscore sphere. Anyway, now when I run the game, we're going to see pretty much the same thing that we had before because, as I said, I'm not applying normal mapping yet. When I hit the spacebar to show these values, we can see that we have ourselves not only the red normal vectors popping out of each of these triangles, but we also have a green tangent vector and a blue bitangent vector. Or it might be the other way around. I don't remember which colors I gave them. You can see that on the sphere they're pretty regular. On the sword and the sheath, they are a little bit more, clustered together where there's more like dense geometry. Let's see. So you might also notice that if I were to take like a freeze frame at a convenient spot where it's easier to see, not all of these vectors are actually like orthogonal to each other, which is kind of a problem because that's kind of what we want. That's kind of how we want our TBN vectors to be. We want them to all be at 90-degree angles to each other. To take care of that, you could do another step where you calculate the tangents and bitangents where you treat these values up here as sort of like intermediates, and you could say the like tangent for real is going to equal the cross product of the normal and the bitangent, and normalize that, and then the bitangent for real is going to be the cross product of the normal and the tangent for real, and then you could do this to make sure that they're all at 90-degree angles to each other, right? And Feather really does not like me just typing out English sentences in the code editor. I'm not going to do that now. I just wanted to mention it because you might have noticed something a little bit funny about the vectors in the the demo scene. I'm also going to. I did say that I would actually show this with the normal map, so I guess now that I've finished with everything else, we can do that. All right, we've got normal mapping on that sphere, more or less. We can also see that if we look at, for example, the Master Sword sheath, we can see the effects of the normal map on different parts of that material, the sword itself. So that's working as intended, more or less, which is a good thing. The same way that you can smooth a vertex normals, the same way that you can take all the vertex normals and just average them on connected vertices. You can also do that with tangents and bitangents if you want. Again, I'm not going to do that in this video because that's kind of a tedious process, and I'm sure this is already long enough. But I just want to shout that out. I also mentioned in the beginning that once you have the normal vector and the tangent vector, you can just do a little cross product magic to get the bitangent. And if you want to save a little bit of time computing this, and if you want to save a couple of bytes per vertex, you could just omit the bitangent and calculate it in the shader. Let's see what else. I believe it is also possible to calculate tangents and bitangents in the shader directly, the same way that you might calculate normals in the shader using the very same texture coordinate gradients using the dfdx, dfdy shader functions, but I don't know, maybe I'll make a video on that someday. Not sure if that's really needed, but it's a thing you can do with math anyway. And lastly, all this, calculating tangents, this is something that you really should not do in an actual game. You really should do what I did in the last video and compute these ahead of time and store them in a file, and then just load the file into video memory with the vertex create buffer from buffer function. It looks reasonably fast when I do it here, but there's only a couple dozen vertices in all these shapes, a couple hundred vertices in the sheath maybe, and if you're doing this with hundreds of vertex buffers that contain thousands of vertices each, you're going to find that computing this for every single one of those is going to take a little while, and there's really no reason you have to do it at runtime. You might as well just do it ahead of time, and you might as well you might as well just store it in a file ahead of time. My GameMaker 3D multi-tool called Penguin, I would like to implement a tangent and bitangent feature into it, like calculation for that, so that you could say that as a vertex buffer. I've been putting that off for years, and I'm probably going to have to put it off at least until after MagFest this year, because I don't have time right now. But something like that is something that you might use to pre-process your 3D meshes ahead of time, so that you don't have to do any. You can do minimal processing with them when you load the game. Anyway, I'm going to end this off here. My name is Michael. I like wizards and dragons and making games. I try to post about 2 game dev videos a week. One tutorial like this, and one let's make a game. Currently a 3D Zelda-like wizard game. I know that I've been a little bit off the schedule with this recently. There have been a couple of videos which I decided at the last minute that I could have done better and that I'd like to redo, so they had to wait a few days. Which is a little annoying, but I'd rather do that than post a video that's just a little weird and awkward. So sorry about that. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. And if you felt like contributing, I definitely would appreciate it. Otherwise, I hope you all found that useful, and I will see you all later. Special thanks to DJ Gibbles, Edward Holt, GameMaker, Manta Ray, Syndra Larson, Squarecrow, VitroV, and Zenjamin for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.